Okay. 7 minutes late, that's great. We can get some time for this. Thanks everybody for coming. We're very excited to have our very own Shiyun Wang, who's going to tell us about row strict dual immaculate, maybe symmetric functions, but maybe just I'll find out.
Okay, so today I'm going to introduce you the row strict dual immaculate function. And actually we define this new basis for the quasisymmetric function from both the combinatorial aspect and also we build zero-Hecke algebra on the function in the representation theory context. And these are joint work with Elizabeth Nies, Sheila Sundaram, Stephanie Wallenberg, and Julian Vega. Okay, so before we go into the quasisymmetric function, I want to start with the symmetric function. Just quickly go over because we know that for the symmetric function, there is a very important basis, Schur basis. And it is not only combinatorial, it is a generating function for the semi-standard and tableau. And also in representation theory, it also has closely connected to, it is the irreducible representation for the general linear group, and also it is a probability calculus for the irreducible representation for the symmetric group. So I want to start from there. So quickly go over the Schur function is the generating function of the semi-standard and tableau, where so we use the so for example, we have a partition and we actually use it from bottom to top. So in the shape of 4, 4, 2, 1, you have stack of boxes following that shape, and then you fill the boxes with row weakly increasing numbers and column strictly increasing numbers. And the content monomial is corresponding to the x1 cube. For example, you have 3 1s, and then you have 3 2s, and then that contributes to the x2 cube, and so on. And the next an important observation is that we can actually kind of transpose the semi-standard and tableau, and then we can generate the same as lambda to read through a semi-standard and tableau in the shape of lambda prime. So for the previous one, to find still the S lambda 4322, we can 4421, we can use the tableau in the shape of 4322, and then basically now we have weakly increasing columns and strictly increasing rows. So we're going to use this idea later on the composition tableau. So so after the Schur function in the symmetric basis, the Schur basis, the symmetric function. Now we have a quasi-symmetric function, and actually people start to do research on all kinds of Schur-like bases in the quasi-symmetric function, and we're trying to look for the analogs compared to the property of the Schur basis. So a quick review for the definition of the quasi-symmetric function. It is a full power series where if you look at 2 terms in the function, then the coefficient of the function for x1 through xk in the power of a1 through ak. If you take any permutation for the subscript 1 through k, such that ai to ak, I1 to ik is a strictly increasing sequence of numbers, then it should have the same corresponding powers. And these 2 terms should have the same coefficient in the function. So here is a very simple example. Say if we only have 3 variables, then the F is quasi-symmetric because you can replace the x1 square x2 with 1 3 or 2 3 for the subscript, but they have the same shape of power. But the g of x here is not quasi-symmetric because we're missing x2, x3 in the power 2 and 1. So that's the quasi-symmetric function. So now we have a quasi-symmetric function, and then if we it is actually an algebra of, so we use the QCM to denote the algebra of quasisymmetric function. And it is the direct sum of all the QCM graded by their degree. And for each QCM n, we can view them as a vector space of dimension 2 to the n to the 1. And then to introduce the other basis for a quasisymmetric function, we need the composition. So a composition is a sequence of positive integers that sum to a fixed integer n. And there is a bijection between the composition to the subsets of 1 through n minus 1 in the ways, for example, if we have a composition 2, 1, 2, 1, 4, then the corresponding subset of, so they sum up to 10, and then the corresponding subset of 9 is, you have 2, and then 3 is the first sum of the first 2 entries, 2 plus 1, and then 5 is the sum of the first 3 entries, 2 plus 1 plus 2, and so on. So we got a set 2, 3, 5, 6 of 1 through 9. And now people discovered a lot of different bases for the quasisymmetric function. The regular ones like monomial and Poisson basis, they are just analog to the basis in the symmetric function. But there are also a family of bases where we call them Schur-like bases. For example, we have the fundamental basis, such that the f of alpha is indexed by all the composition of n. And it is a sum of terms where each term you have weakly increasing sequence of subscript of the x, and whenever the ij less than ij plus 1, or whenever j is inside of the subset corresponding to the composition there, then their subscript should be different. So that's the fundamental basis. And other than that, we also have quasisymmetric Schur function, and inside of this family, we have a lot of variations on that. We will briefly introduce later. We have the row-strict quasisymmetric Schur function. We have the Young quasisymmetric Schur function. And also, there is a basis called immaculate basis. And our work actually relies on the discovery of the immaculate basis.
Okay, what do you mean when you say Schur-like basis? What properties are you kind of saying this?
So I think I will give you more properties on this basis. So there are analogs compared to the Schur basis in the symmetric. So that's why we call it Schur.
But analogs in what way? Like, how are they analogous?
So for example, you may have
like, for example, the fundamentals. How are the fundamental, like, what do you, I'm just trying to understand what you mean by, because I wouldn't consider the fundamentals Schur-like, so I'm trying to understand what.
because for lots of for all of those bases, we can get them combinatorially. They are all generating functions of some certain type tableau, and which are similar to the Schur. Like, yeah.
Okay.
So I will do the definition out of it. So, for example, the very first one, the poset Schur, the Young poset Schur. So the Young composition tableau is a tableau in the shape of composition. So the Schur has the shape of partition, and now we have a tableau in the shape of a composition. For example, we still start from bottom to top. So this is a composition huge 3, 3. And we do a filling of the tableau with positive numbers, where this kind of tableau, we follow the rules that all the rows are weakly increasing, and only the first column is strictly increasing, and we don't have no requirement for the strictly increasing for other columns. So that's kind of an analog to the tableau of Schur function. The second and Young tableau. And also, we require a triple rule such that if you have a shape of entries in this way, then if A is greater than or equal to B, then A is greater than C. So we have to make these three requirements satisfied in the tableau. And also we can read the content monomial from the tableau in a similar way as we read the semi-standard Young tableau. And so the Young quasisymmetric Schur function is defined as the generating function of such tableau. So it's just a sum over all such kind of valid tableau, and the term is the content monomial. And now people do similar things to rotate that tableau, just as I mentioned the observation for the standard Young tableau. So the requirement is a little bit different because after you rotate, we require that it is a tableau in the shape of composition, and all rows now is strictly increasing, and the first column is weakly increasing, and you still have the triple rule, but we modified it a little bit. If A is greater than B, then A is greater than or equal to C. So the row strict poset is the generating function of this kind of tableau. And also XD is just the content monomial.
Are there two types of tableau in bijection?
Row strict tableau and composition tableau, they're the same number of them.
Yeah, the previous one, like you just transpose the semi-standard condition. Okay, that changes nothing about.
Yeah, because
combinatorics is different here.
yeah, because people can expand the Young quasi-Schur in terms of the row strict version.
Like positive coefficient?
Yeah.
Okay.
Yeah.
So there are more of these.
And now their connection to the Schur function. The first result is expand the Schur function in terms of the Young quasi-Schur, and then also the following work in a similar way we can also expand the Schur in terms of the row strict.
Wait, hang on.
So
Wait, is it always true that S hat is a positive sum of the R S hats? Guessing no. I think I misunderstood your answer to the previous question. So the S hats are the young ones, is that right?
I think we do have
So the young ones are always a positive sum of the other ones. I'm confused.
Yeah, because there are the same number of lenses.
Not quite, because it conjugates at the bottom, but you could always choose lambda so that one of these has more terms than the other. But you can do it like, you just switch it, right?
So wait, what was alpha hat was the sort?
Alpha tilde sorts to lambda, or alpha tilde sorts to lambda conjugate. But the problem is that you could, just by choice of lambda, you can make either one of these have more terms than the other. So I don't see how.
Yeah,
either of these
so,
positive together.
yeah, so, okay, so they're the same number.
That's what it is. Okay, so they're not the same number, and neither is actually strictly bigger than or strictly smaller than the other.
Here are just a list of a few more results that in recent years that people found of these functions connected to the Schur function. For example, we have a literature rules, and people also constructed the zero-hacking modules on the quasi-Schur and row strict quasi-Schur, and also there is an analog of the RSK, and also Monahan and Nakayama rule for these functions.
I don't have Yamas for power sum.
So multiplication by a variable, or what is it? For a power of a variable.
Yeah, by power.
But by the actual power sum, so kind of like the top one, but replacing S lambda with P lambda. Is that what you mean? I guess it doesn't matter. Sorry, if you're not checking out the results, whatever.
Okay, so now, there is another Schur's-like basis, which is called the dual immaculate functions. So the difference for this kind of tableau is compared to the Young Quasisymmetric Schur tableau, we just simply drop the triple rule, and we still have first column strictly increase and all the rows weakly increase, but we don't have that triple rule. And this is an example. If we have immaculate tableau in the shape 3, 2, 4, 1, 2, and then we just have all the entries. We could increase in rows, and the first column may strictly increase. And then the dual immaculate function is the generating function of this kind of tableau. So, some properties for the dual immaculate function, we can first standardize the tableau by following a certain reading word. So for example, you have 1, 1, 2, 2, 2, then you read from left to right, and then you standardize it 1, 2, 3, 4, 5, and then basically read from bottom to top and left to right. And then you got a standardized immaculate tableau. And then
can you have the same, can you have like 2 2s in a column, for example?
except the first row, then you can have.
But I could have like a column of all 2s, but not the first row.
Right, right.
Okay, thanks. Because your example is strictly increasing in all.
Oh, yeah,
columns, So it's okay.
You can do the same thing, or you can even have decrease thing. That's fine.
Yeah, okay.
Yeah.
Repeats are allowed, decrease are allowed. It's just crazy. Okay, cool.
And from the standardized tableau, there is a descent set of the standardized tableau, where it is a set of all i's such that I plus 1 is strictly above I. So you got a set from the standardized tableau. For example, in this case, you got 2 because 3 is up above 2, and then 5 because 6 is up there, and then 8 and 10. So the Bergeron, Serrano, Zabrocki. So because our result relies on their papers a lot, so from now on I'll just use the BBSFD, their initials, to refer their papers. So they expand the dual immaculate function in terms of the fundamental basis, where this is the descent set that we just got from the standard tableau, and then this is a composition responding to that descent set. Okay, and here are some related results. We can also expand the Schur in terms of the dual immaculate basis, but it's not a positive expansion. And now we can also expand it in terms of the Quasisymmetric Schur, and it is a positive expansion, and the coefficient is a set of tableaus satisfy several conditions.
I'm trying to part the standard 15. So we're summing over partitions. Sorry, you're summing over permutations of K, where K is the length of lambda.
Yes,
And you get your sign from the sign, obviously.
sign is
Yeah.
for the computation. And
And then
keep along that.
that's cool, okay.
It's like it's over two.
It totally does, yeah.
And if any entry is 0.
But that means for the kind of like the H's, you don't really have the extra condition, right? That's cool. Okay, sorry.
So I guess now it's very natural to think about because the Young Quasisymmetric Schur, and we have the row-strict version of Schur, and then now it's natural to think about, do we have any row-strict version for the dual immaculate basis? So we start from combinatorial meaning for that. So we try to just take the tableau, dropping the triple rule, and then we got the same tableau as the row-strict Quasisymmetric Schur, but dropping the triple rule. So now you have all rows strictly increasing, but the first column needs to be weakly increasing and no requirement for the other columns. And then we define the row-strict dual immaculate function as a generating function for all of this kind of tableau. So we get those similar words. We standardize this tableau by using the different reading words. So basically we read them reversely from right to left. So you can standardize that. And we define a different descent set such that I plus 1 is weakly below I. So you also get a descent set from there. And then we can prove that the Roche-Dury-Macron function also expands to the fundamental, expand positively to the fundamental basis, such that you got the composition from those descent sets. And so one important observation is that the descent that we got compared to the descent set from the BBSD, they actually complement to each other. So by knowing that fact, we can immediately get basically all of the results from the Dury-Immaculate function because
Psi is the.
sorry, psi is okay. So first of all, they proved that the Dury-Immaculate function is the basis for QCM, and we proved that psi is the involution in poset-symmetric function, sending F alpha to F alpha complement. Yeah. So we proved that the Roche-Dury-Immaculate is the image under the sign, and because of this theorem, then basically we can just apply phi to all of the results for Dury-Immaculate function, and then you got the analog result for the Roche-Dury-Immaculate function, and it's very easy to prove that it is a basis. Okay, so we got that from the we got that combinatorially from the tableau, and now we want to build the function more solid. So we start to look at the dual of the quasisymmetric function in the noncommutative symmetric function, the NCM. And we also want to define the dual of the Roche-Dury-Immaculate in NCM as what the BBSSC did. So we define the Roche-Immaculate in NCM to be the dual of Roche-Dury-Immaculate. And then since they are the Roche is the image of psi, then in the NCM they should be also the image of psi of immaculate basis. And I think I will skip the technical stuff a little bit, but basically we use a operator because for the Schur function we can also use the Bernstein operator to find the Schur function. And then the BBSC, they modified that Bernstein operator a little bit, and then they found they used that operator to define the immaculate basis. And now we also modified operator according to our function, and then we got this B.
You just use E's instead of B's. You're just using E's instead of H's.
Yeah, basically. And then
Makes sense.
you can find the Roche-Immaculate basis by applying that operator on the identity. Okay. So after that, we start to think that can we have a skew version of the Roche-Immaculate function, and then we almost use a very similar poset from the BBSSD, but we do a different labeling for the numbers. So let me explain a little bit. So this is a start of the poset of composition, and then you start from empty and then one box, and then you increase them. And then, for example, if you decrease from this line to this line, the red past year, you're taking off one box at a time, and the number marked above the arrow means that is the row where we take off the box. So since we count from bottom to top, so for example, we take off this one, and then that is on the first row, so you got number 1, and then next we take off one box from the second row, you got a number 2, and so on. And then we can get a shape as this one. So these are the 3 boxes that we take off in order, and then we number them in the reverse order. So this is the first box we take off, this is second, and this is the last one. So in that way, we can get a skew shape of standard skew immaculate tableau filled with all positive integers. And by the way that we take off the boxes, we can make sure that they all have increasing rows, and if we have the first column, they're also increasing from the bottom to top. And here is a more detailed example. Say if we have a composition 3, 2, 3, and then we want to take we have alpha minus beta equals to 3, 2, 3 minus 1, 1, 2, then those numbers will give us a term in the skew immaculate function. So for example, this is 4, so this is going to be the first box we take off, and then 3, and then 2, and 1. So from there, we can also read the descent set as before. And also we can use the same tableau to read the descent set for the skew immaculate function. And combinatorially, the skew version, they are just the generating function for this kind of skew tableau. So again, some similar properties that we can find expand to the fundamental, ranging over all the standard skew immaculate tableau by using different descent set. And so after that, we started to think another approach to define the skew restrict immaculate basis, because earlier we just got a combinatorial meaning for that. So recall that the QCM is a Hopf algebra graded by degree as a direct sum of QCM n. And in the Hopf algebra, we can use the coproduct to write the coproduct of the S alpha equals to the tensor product of two elements, and one we call it a skew-shaped element. We don't know what it looks like at this point, but and then the sum is ranging over a pair of indices. And we actually prove that this skew element agree with the definition that we got from the tableau, the generating function of the tableau. So so these two definitions agree, and this fact allows us to derive more properties for our function. For example, the BBSC proved that Schur's function expands to how it expands to the immaculate function, but and with the Hopf algebra approach definition, we can use the coproduct to find out the expansion of the skew-Schur function into the skew immaculate function. Okay. And I mean, all of those results, similarly, you can just apply the sign to get the version for the skew restricted immaculate function. Okay. So the first part, we focus mainly on the combinatorial effects of this new function. And then the second part, we move to look at the representation theory context. We built a zero-Hecke algebra on the new function. It turns out that this module, the restricted immaculate function is a characteristic of the module that we construct. So let me start with some basic background. So we know that the symmetric function can be generated by the adjacent transposition. Si is a transposition I plus one. So subject, we have all of the relations there. Si square is identity, and then Si, Sj commute. And Si plus one, Si, and then also commute among those triples. Then the zero-Hecke algebra is also defined with those generators pi I with similar relations, such that pi I square is pi I, and pi plus one, pi I equals 0. We can commute those elements, and then pi I, pi j commute. The zero-Hecke algebra admits the two n-1 irreducible one-dimensional module L alpha, where the alpha is indexed by the composition of n, and we define that the characteristic of the L alpha is the fundamental basis at alpha. Okay, so now here is how we define the action on our tableau and construct the module. So we define a row strict immaculate action on the generators pi I on all of the tableau that we have, such that only if when I plus one is strictly below I, then we will swapping I and I plus one to get a new tableau. Otherwise, if they are in the position other than this condition, then either we map it to 0 or we stay with the tableau T. So for example, so we can randomly pick one, for example, this one, and basically you just go through all the numbers. We can only get a new tableau, for example, pi 4, because 5 is below 4, so you're swapping the 5 and 4. But for the other, and then you also have pi 6 by swapping 6 and 7, but you cannot have any other new tableau because 2 is about 1, so you don't have new thing. It's either 0, or if they're on the same line, then it's 0. If it's about, then you stay there. So for one shape alpha, we can actually write out all of the elements that we can generate, and then actually we prove that we can always find a minimum element there. So the minimum element will always look like this. So you have an increasing from 1, 1, 2, 3, and then you go right 4, 5, and then you go down 6 and 7. So if you have more up there, then you should have you go up with a consecutive positive number 1, 2, 3, and then you go with from left to right for each row. So those will be the minimum element for all alpha. And then you can generate the poset from there, and it is a great poset, and then up to there we can always get a maximum element in our poset, such that they always counted this way: 1, 2, 3, 4, 5, 6, 7. So you count from left to right, from bottom to top. And the partial order in this poset is whenever this tableau covers that tableau, by swapping the I and I plus 1, then we say this one is less than that one in the poset. So up to there, we got a poset of the tableau. And we do prove that this module is actually a cyclic module, an indecomposable module. For example, if you randomly pick any element, we can always find that element is cyclically generated by the minimum element here. So I think this is too small, but I'll read it for you. So for example, if we pick this one, 1, 3, 2, 4, 5, 6, 7, then it can be generated by the bottom element here by apply all of the pi. So paths would be pi 6, pi 5, pi 6, pi 4, pi 5, pi 3, pi 4. So all same thing for all the other elements, they're cyclically generated. And actually, the quasisymmetric characteristic of that whole module would be our rho-strict dual immaculate function. And also we can recover the original dual immaculate function also from our poset. And in that way, you just take the top element and then you take the dual of the poset, you generate it again, and then and the characteristic of that dual poset of this would be the dual immaculate function. Yeah, so we have the S0 is the bottom element, and then the S row would be the top element. And this module is cyclic, generated by the minimal element, and is decomposable. And more thing to go back. And actually, we took a closer examination on this poset, and we found some interesting thing is that, for example, the red tableau there, 1, 2, 3, 4, 5, they form a closed interval in the poset. And if we observe them, they have the similar property that they have all their columns increasing, cyclically increasing. And not same for the other tableau. So they form an ideal in the poset, and this is no accident because it turns out that the quasisymmetric characteristic of this ideal, so this submodule, is actually connected to the extended Schur function defined by Semi and Schur. Yeah. And it's not exactly the extended Schur, but it's the image of the extended Schur under the psi involution. And yeah, and we also consider, say, the blue tableau there is the whole module quotient by the red tableau, and then we got a quotient module, and we're considering the properties for those. So it turns out this poset has a remarkable property that it really helps us to get a lot of Schur-like bases involved.
Is that poset a crystal or something like what? Yeah.
Not like string or that. It's sort of like it's like a offsetter graph on the symmetric, right? These are sort of like looking at reduced words, like kind of changing it. But that's what it is. But for the zero hack algebra instead of for
Yeah, so last theorem is saying that oh, I forgot to mention that the same thing for the set of the red tableau, again, we can prove that they are cyclic and also indecomposable, and the generator would be the bottom one. And yeah, we name it as column because it always has a shape that you label it from bottom to top along columns. So 1, 2, 3, 4, 5, 6, and 7. And for all other shape of composition, the bottom elements always look like this. You count along columns from bottom to top. And so this is a cyclic one, and also it is an indecomposable one.
Maybe my question was, what are the ranks? If any?
What is the?
This
Ranked
appears to
invertible.
be a ranked poset.
Yeah.
The way you've drawn it, it appears to be ranked. Well, this one
Yeah.
definitely is, but in general, perhaps it's ranked. And if so, then what is the rank? So the naive definition is the rank is the distance from your S0 value.
Yeah.
But does that, is there some combinatorial way that we can see that? Could we measure it based on like some pairs of some, I don't know.
Inversions or something like that.
Yeah, there's some analog inversion.
Yeah, I think, yeah, they are graded actually by, the inversion of the reading word of the tableau. So we can, yeah, we can read them reversely. Yeah, so for example, this one, we have the reading word for that, and then
Exactly.
you find out all the number of inversion, and then that will be the rank.
Okay, and if that means something. The rate.
But it's inverted.
However, it's a dimension of a Schubert drive.
Some more complicated structure.
Yeah, I think I go a little bit quick and then, but that's all, that's all.
Yeah, so we got half of here, 34.
I know, it's still like, because we can bring back the example.
Well, yeah, but,
Okay,
Yeah, it doesn't all fit on the same thing.
yeah, I know, I totally get that stuff, yeah. Great, this is like your diagnosis.
those are all of my demands, they thought, okay, saw that process.
Okay, now if you want to advance it with class.
That's all. That's all.
All right, does anyone have questions, more questions for Shiyun? Because that's like beautiful slides with beautiful pictures throughout, so we could get back around to their opinions, but does anyone